Dear colleagues, this is a presentation on the paper entitled Controllability and Period Survivability of Cooperative Reciprocal Strategies in Smart Grids. Authors are Vadim Romanuk and Larissa Radzikovska. The presenter is Vadim Romanuk. Sustainable performance of smart grids requires controllable cooperation among agents. Cooperations facilitate the equality of power balance, whereas the faction may violate it irreversibly for a period of time. Despite factual decentralization, governmental regulators do influence smart grid infrastructure by imposing legislative and economic constraints and requirements. Issuing from the need for controllable cooperation among agents in smart grids, the goal is to suggest a method of determining sustainable strategies for efficient cooperation with plausible reciprocity. Once the grid system is perturbed, such cooperative reciprocal strategies must recover the system by bringing it to the normal regime. To achieve the goal, we need to fulfill the following tasks. Model the energy unit price change in the payoff matrix evolution. Determine the most influential parameter such that its adjustment is the most tightly connected with inducing the cooperative reciprocal strategies. Third, develop an algorithm of mitigating the factions to a tolerable rate whose returns are the best parameter value and cooperative reciprocal strategies induced by that value. And given any criteria of the strategy applicability, the period of survivability of those strategies must be estimated. The energy unit price consists of the standardized part P0 equals 1 and observably random fluctuations whose causes are non-traceable. The price is affected by the factions whose rate is calculated by 1. Then the price linearized model is given by 2. At each time slot t, the agent chooses between cooperation, denoted by C, and defection, denoted by D. The payoff matrix at time slot T is 3, where R of T is the agent's payoff when both the agent and the opponent cooperate. S of T is the agent's payoff when the agent cooperates and the opponent defects. S of T, when the agent cooperates and the opponent defects. Q of T, when the agent defects and the opponent cooperates. U of T, when both the agent and the opponent defect. Time slot T equals 0 corresponds to the situation of a smart grid normal regime perturbation. This is given by inequalities for. This actually provokes a short-term growth of defective behavior, which can be mitigated only by achieving inequality 5. The payoff matrix entries evolve with occurrence to 6, 7, 8, 9, where we can see another two parameters controlled by governmental regulators: cooperation rewarder beta and the faction-based price deviation corrector eta. The grid interactions among agents, consumers, and prosumers are modeled with Axelrod iterated prisoner's dilemma tournaments. Due to agents cannot update their strategies instantaneously, we introduce behavior inertia but by 10, 11, 12. So, if the last strategy update of agent N happening at time slot T star, then at time slot T agent N updates its strategy only if inequality 13 holds. This is the flow chart of the algorithm of determining the best regulative configuration for smart grid recovery. In fact, the algorithm attempts to solve a stochastic multi-objective constraint optimization problem. The algorithm is implemented in Python. Here is an example of how the defection rate, figure 4, is mitigated down to zero level, although the price volatility, figure 5, does not much change. The mitigation is done by recovery strategic trajectory, figure 6, which affects defections while not affecting much the price and payoffs, figure 7. And in this case, the grid is stabilized within 6 time slots, so the period of recovery is 6, period of survivability is 30, figure 8. In another example, below, long-term stabilization is currently impossible, despite very short period of recovery, which is 3 here. Period of survivability is just 9. So the conclusions are as follows. The developed iterative algorithm determines a smart grid recovery strategic trajectory. It is an attempt to solve stochastic multi-objective constraint optimization problem where the free parameters are iteratively optimized. The most influential parameter is the price deviation corrector. The recovery strategic trajectory is mathematically very complex object, whose principal random components are ordered cooperative reciprocal strategies and the periods of recovery F and sustainability, or rather period of survivability. Yes, you can call it sustainability. The solution is found within 10 iterations or fewer. This computation is actually a virtual run immediately follow the perturbation, and this run result, which is actually a recovery strategic trajectory, returns the smart grid system to a normal state by minimum possible intervention. And finally, as the period of survivability expires, an update of the strategic trajectory may be needed. Thank you very much for your attention.